Okay, 7.1 angle formulas. So compound angles can help solve trigonometric expressions, allowing for large angles to be broken up into smaller components for exact calculation of trig ratios. Okay, so we have a bunch of compound angle formulas. I'm just going to go over the first three for addition, and then at that point, you guys can take a look at like the subtraction and then the other formulas, okay? So this is what happens, okay? So say we had sine of a big angle. So big angle. What we can do is like, we're gonna generally look for pi by 4 angles and then pi by 3 and pi by 6 angles as well, okay? So we're going to see if we can break that big angle down into two smaller angles. Then how this works is like sine A plus B is going to be equivalent to sine A cos B, right? And like we're obviously going to be subbing in the angles there, and then plus cos A sine B. Okay, and then again, we're plugging in the values of the angles into A and B. Okay, there's going to be a cos A plus B, and then this is the expansion of it. Cos A cos B minus sine A sine B. Then we also have one for tan, okay? And then you can follow along. So we have the compound angle formulas for addition, which obviously is like A plus B, okay? And this time we don't need to, like we no longer need to only use 0, pi, and 2 pi. We can actually use just like any angles. We could do like pi by 4 plus pi by 6 or something, okay? And that's okay. We can also do the subtraction of those two angles. So like the difference between two angles will give us like the big angle that we're looking at. And then we also have something called double angle formula, okay? So it's so important. I want to stress this. Oh, this should have been down. It's okay. I want to stress that like sine A plus sine A, this equals 2 sine A. It does not equal sine of 2A. This here is different because this here is inside that bracket. Like this is part of the angle, whereas this in front represents, like I kind of want to call it a vertical stretch by a factor of 2, or like 2 of sine A plus sine A, right? So these two things are very, very different. So just be careful of that. Whenever we're working with like sine of like this double angle here, 2A, cos of 2A or tan of 2A, I think it's way better to substitute in an equivalence for that. Okay, and then this just says like when a single angle theta is doubled in value, it can be represented as 2 theta, okay, in these double angle formulas. Okay, so let's take a look at solving for ratios using compound angle formulas. So I did this in degrees, but we can do like likewise in radians. So assess whether the angle is from a special triangle. I always try, like I try to keep them to special triangles, right? So what we're looking for is like 30, 45, or 60, which is pi by 6, pi by 4, or pi by 3. Okay, we're looking for those angles or any angle that it adds up to these or subtracts to these. Okay, but if not one of the three angles, what we're going to do is we're going to rewrite that big angle as the sum or difference of two angles. Again, we're trying to use these three plus 90 degrees, which is pi by 2, 180, which is pi, 270, which is 3 pi by 2, or 360, which is 2 pi. Okay, we're trying to use any of these, and we're trying to rewrite that big angle as like a sum or difference. Okay, so those two kind of go together. Number 1 is more in unit 6. Now we're venturing out. Okay, so what we can do is we can use the compound angle formulas to expand our expression, and then we can simplify the same way. We can cancel out, collect like terms, sub in known values. Okay, so a couple different approaches to this. Example 1, determine the exact value of the following. Okay, so we're going to start with sine 75. So when I look at 75, 75 is definitely not from one of our special triangles. Okay, we're going to I'm going to teach this in degrees and then we're going to toggle over to radians, okay? So if we have 45 and 45, okay, then it's 1, 1, root 2. And then if we have like 30, 60, and then obviously 90, 1, 2, root 3. Okay, so here are the two special triangles in degrees. Now 75. Here's a hint. Whenever I see that 5, I know it's not going to be like a 30 and a 60, because if you think about it, like we need a 5 in there. So likely it's going to have something to do with the 45. So for this one, I'm looking at it, I'm like, okay, well, 45 plus 30 is going to give us 75. So what I'm going to do is I'm going to break this sign down, sorry, not the sign, but the 75 down into 45 plus 30. Okay, I'm going to erase this, and we're going to come back to it, close to 15. Okay, so now let's actually expand. Okay, so if we have sine of a plus b, what are we using? Okay, so we're going to use addition, so sine a plus b, right? So 45 is going to be our a value, and then b is going to be 30. So we can write sine a, so we have to write sine 45, cos b, so cos 30, plus sine. So for sine, for the addition, the signs match, plus plus, that's fine. Cos a, so we're going to go cos 45, and then sine b, so sine of 30. Okay, so here's the expansion. Now, what we're going to do is we're going to sub in the ratios. So this is just like what we saw in the last unit. I'm going to get 4 ratios, and I'm going to sub them into these brackets. Okay, so sine of 45 and cos of 45 are the same, right? Because 45 and 45, if you actually think about it, the opposite and the adjacent are the same, and then obviously the hypotenuse always matches. So sine of 45, just don't forget SOHCAHTOA, is going to be 1 over root 2. Cos of 45 is also 1 over root 2. Okay, now 30, I'm going to label this as opposite, this is going to be adjacent, and this is going to be hypotenuse. Okay, so cos of 30 is root 3 over 2, and sine of 30 is 1 over 2. So now we just multiply. So remember, when we multiply fractions, we multiply the numerators, okay, and then we multiply the denominators. So 1 times root 3 is root 3. Root 2 times 2 is 2 root 2. 1 times 1 is 1. 2 times root 2 is 2 root 2. And this already has a common denominator, so we can just rewrite this as 1 plus root 3 over 2 root 2. It's just common to write this root afterward. Okay, example 1, again, we already did A. Now let's move on to B. Determine the exact value of cos 15 degrees. So again, every single question that I do, I go to the side of my paper and I write out the special triangles, okay? 1, 1, root 2, then we have 30, 60, 1, 2, root 3, okay? So cos of 15. So I'm looking, and again, we have this 5 here, okay? The 5 triggers me to do a 4, okay, like 45, sorry, to do the 45. So I think 60 minus 45 equals 15. So I'm going to actually write an equivalence of this. This is equivalent to cos 60 minus 45. Okay, if we take a look at like the compound angle formulas for subtraction, okay, so I just put it up here, cos A minus B. So A is going to be our 60 minus our 45. So we have cos A cos B. So we have cos 60 cos 45 plus sine A sine B. So sine 60 sine 45. And if you notice for subtraction for cos, the sign in here, the subtraction, is actually opposite to what's in here. So that's addition. Okay, So let's get rid of this. So let's take a look at labeling these two special triangles in relation to the 60 and the 45. Okay, so this is going to be opposite, adjacent, and hypotenuse. Okay, the hypotenuse doesn't change. And then for 60, we're going to do it relative to the 60. So this side is going to be opposite, the root 3 this time. Okay, adjacent and hypotenuse. So all we're going to do is have 4 brackets, and we're going to fill in the ratios. Okay, so cos of 60, 1 over 2. Cos of 45, 1 over root 2. Sine of 60 is root 3 over 2. Sine of 45, 1 over root 2. So numerators times numerators, denominators times denominators. Okay, so we have 1 times 1 is 1. 2 times root 2 is just 2 root 2. Root 3 times 1 is root 3. 2 times root 2 is 2 root 2. Okay. Collect the numerators, 1 plus root 3 over the denominator, over 2 root 2. Okay, now cos of 225 degrees. Okay, so again, we're looking at 30 degrees, 45, 60, and then we're looking at the 180, the 270, the 360, oh, and the 90. So what to add up to 225? Well, again, as soon as I see that 5, I'm thinking 45. It's the only angle that we have in like a special triangle or like one of these key, like these main points, these critical points, that has a 5 at the end. So I'm thinking 45. So if you think about it, I'm like, okay, well, what's 225 minus 45? Like, what's actually left over? Does that give us a good number? Yeah, it's 180. So essentially, I'm gonna say that this is equivalent to cos of 180 minus 45. No, plus 45. There we go. So I went ahead and I pasted the addition for cos A plus B. So A is going to be 180 and B is going to be 45. So cos A cos B, cos 180, cos 45, minus sine A sine B, sine 180, sine 45. Okay, so we know that we're going to have 4 numbers, 4 ratios, right? And we know cos 45 and sine 45. I mean, I don't have to draw that again. I have this memorized. It's 1 over root 2. Okay, so cos 45 and sine 45, both the same, because we have 45 and 45 for these two angles here. But when we get to 180, this is a little bit different of an approach. Okay, so if you remember the sine curve, sine x looks like this. So if you're thinking about 180, 180 is here, sine of 180 is 0. So we actually sub in 0 right here. And then if you're thinking about the cos curve, you're going from a maximum, okay? So 180 is it's gonna be a minimum at 180. So it's gonna be -1. So this would be -1. So these two numbers multiplied will give us 0. Okay, and even though this gives us 0, don't quit after you see that this is 0. Still fill this in for like full marks. Okay, and then what's -1 times 1 over root 2? Well, that's just -1 over root 2. And that's the answer. All right, now we have D, tan of -5 pi by 12. So when I'm thinking about this number, so first of all, it's in radians. So now I'm thinking pi by 3, what is it, pi by 6, pi by 4. Okay, I'm thinking pi by 2, pi, 3 pi by 2, and 2 pi. Okay, those are my angles that I'm thinking of. I'm not going to draw the special triangles yet. Okay, example 2, simplify each expression. So taking a look at this, I do not want to draw 4 of these and put brackets for each ratio and solve. Like, this is a lot of work. But if you actually read this, And you see that this is cos of 7 pi by 12, cos of 5 pi by 12, plus sine of 7 pi by 12, sine of 5 pi by 12. You can notice that we have two 7 pi by 12s, and we have two 5 pi by 12s. And we have cos, cos, sine, sine. So let's actually take a look at the double angle formulas. Compound angle formulas, sorry. Okay, so if we have cos, cos plus sine, sine, take a look here. So cos, cos, but this is minus sine, sine. So this is close to it, but that's not it. So let's scroll down. Cos, cos plus sine, sine. Okay, well, that's what we're working with. Okay, we're working with cos A minus B. So essentially, our A value is going to be our 7 pi by 12, and our B value is going to be our 5 pi by 12. So now we have cos of A minus B. That's the formula that we're going to use. These are equivalent, right? This is just the expanded form, so this is expanded. And this is the simplified form. So we can actually go backwards as well. So let's actually start the question. So cos 7 pi by 12 minus 5 pi by 12, which gives us cos of 2 pi by 12, which simplifies to cos of pi by 6. And cos of pi by 6, first quadrant, we're simply looking at the special triangle, and we're going to have 1, 2, root 3. Cos of pi by 6 is adjacent over hypotenuse. I get root 3 over 2. All right, same idea. So we have B, sine 2x cos x minus cos 2x sine x. So if you actually think about it, we have duplicates here. Okay, so angle A would be 2x, and then angle B would be x. So let's take a look at the formulas and line up which one has sine cos minus cosine. Okay, so sine cos minus cosine. So sine cos minus cosine. This is the one we're using. Okay, so this is essentially going to be like sine A minus B. Okay, so let's write it out. So we're going to have sine 2x minus x, and these are equivalent, right? Again, this is expanded. This is simplified. Well, what's 2x minus x? Let's just sine x. Okay, and we don't have any values for that, so that's it. We're done. Okay, example 3. Evaluate sine A plus B, where A and B are obtuse angles. So those lie in quadrant 2. And sine A, okay, so let's talk about A first. Sine A, it's going to be obtuse, right? Because it's essentially like this, is 3 over 5. So sine is opposite. Opposite is 3. 5 is the hypotenuse. And if you remember solving for the other side, it's just Pythagorean's theorem. 5 squared minus 3 squared. So it's 25 minus 9, which is 16. So B equals 4. Okay, so this side is 4. Now B, likewise, is going to be sine is opposite, which is 5. Hypotenuse, which is 13. And likewise, 13 squared minus 5 squared equals the other side. So 169 minus 25 is going to equal the other side, which I believe is 144. So B equals 12. So this side is 12. Okay, evaluate sine A plus B. So A plus B like this, we can't do anything with. But let's take a look at what sine A plus B expands to. Okay, so we're going to have, oh, you know what? I took this straight off the note and it just works. Like it's going to be the same thing, just like lowercase. So sine A plus B equals sine A cos B plus cos A sine B. So let's go ahead and sub in these four ratios. So the thing is, sine A is already given to us. It's 3 over 5. So we can just put that right in here. Sine B is also given to us, 5 over 13. Now what we need to do is we need to find cos B. So go back to B. Cos B is adjacent over hypotenuse, 12 over 13. Now cos A is adjacent over hypotenuse, 4 over 5. And then we just solve. 3 times 12 is 36. 5 times 13, 65. Plus 4 times 5 is 20. 5 times 13 is 65. I get 56 over 65. So sometimes when we have like negative 5 pi by 12, if you think about it, like if you think about this common denominator being 12, 6, 4, 3, 2, all of these numbers, we would have to convert into denominators of 12, right? So we could potentially be like, okay, well, what's pi by 6? Well, that's like 2 pi by 12. Pi by 4, if you think about it, is 3 pi by 12. Pi by 3 is 4 pi by 12. Pi by 2 is 6 pi by 12. Pi is just 12 pi by 12. 3 pi by 2, 2 has to multiply by 6, so that's 18 pi by 12, and that's 24 pi by 12. Okay, those are all the conversions so that we have everything over 12. So now how would we get, we can ignore the negative for 1 second. We're going to take that into account in a second. How do we get to 5 pi? Well, I would say so these two here would equal 5 pi if we added them. So we can take, because like all we're really doing is looking at the 2 and the 3, right? So we can take these and be like, okay, well, this is tan of, and then, but it has to be negative. So negative 2 pi by 12 minus 3 pi by 12. So what we're going to do is we're going to treat A as this negative 2 pi by 12. We're going to use the subtraction formula, and we're going to treat B as 3 pi by 12, but the positive of it, because we're taking into account the subtraction formula. Okay, so let's go with a different color. We're going to go, and I put this on the board here now. So we're going to go tan of negative 2 pi by 12 minus 3 pi by 12. Okay, that's going to equal tan of A, so tan of negative, so negative 2 pi by 12, let's break that down more. Let's break that down back into 2 pi by 12 is negative pi by 6. Okay, and then 3 pi by 12, which is here, is pi by 4, so negative pi by 4. So we'll go ahead and erase this. So this is actually what we're dealing with when we're dealing with these angles. So tan A, so we have tan of negative pi by 6 minus tan B, so tan of pi by 4. And that one's normal because this negative sign is already built into like the equation, right? We did the subtraction. Okay, all over 1 plus tan A. So it repeats here, negative pi by 6, and then tan B, which is tan pi by 4. And then I would be going to the side of my paper and doing me like, okay, pi by 4 is going to be the 1 root 2. And then negative, well, pi by 6, and then we'll just make it negative. That's fine. Okay, pi by 6 is going to be across from 1 to root 3, with this being opposite, this being adjacent, and this being hypotenuse. Okay, since it's negative pi by 6, all that means is it's rotating here, and then this is the C quadrant, so it's just going to be the negative of this ratio. So tan of pi by 6 is going to be 1 over root 3, but it's going to be negative because we're in the fourth quadrant, minus tan of pi by 4 is opposite over adjacent, 1 over 1, so just minus 1. All over 1 plus. Okay, and then these are duplicates. This is a duplicate of here. So negative 1 over root 3. And then this is a duplicate of here times 1. Okay, so negative 1 over root 3 minus 1. We're going to find a common denominator here. So root 3 over root 3. So we're going to have negative 1 over root 3 minus root 3 over root 3. And then that's going to be divided by 1 plus, and then we have negative 1 over root 3 times 1, which is just, so we can just do 1 minus 1 over root 3. So for the numerator here, I'm going to say that it's going to be negative 1 minus root 3 all over root 3, right? We're going to collect these and then put it over one denominator. And then I'm going to write this beside, so divided by, so we can't subtract these, so I'm going to multiply the 1 by root 3 over root 3, right? Like we're just multiplying by 1, we're not actually changing it. So we're going to have divided by, so that's going to be root 3 over root 3 minus 1 over root 3, so that's root 3 minus 1 all over root 3. And because that's divided, we can go ahead and multiply by the reciprocal. So the reciprocal, the root 3 comes to the top, and the root 3 minus 1 goes to the bottom. Those two can cancel because they're divided, and we're left with negative 1 minus root 3 over root 3 minus 1. And we can leave it like that. That's fine. You could exchange these, negative 1 minus root 3 over negative 1 plus root 3. You can also write it like that just for continuity and consistency.